everyone to today's seminar. Today we have Behzad Tahmasebzadeh, who's a postdoctoral researcher at the University of Michigan in the United States. Behzad got his PhD last year at the Shanghai Astronomical Observatory in China, and his research focuses on the dynamical modeling of various types of galaxies to determine their underlying mass profiles, including stars, black holes, and dark matter, as well as their internal structures. In the past years, he developed many techniques for dynamical modeling of large galaxies, and he's currently applying these techniques to a few observations with JWST and NIRSpec. So thank you so much, Behzad, for accepting our invitation in such a short notice. You may start when you're ready.
Thank you very much, Anna, for introduction, and thank you very much for having me. I'm honored to be able to have this chance to talk about my ongoing research in your institute. So I will talk about can you hear me? Everything is okay?
Yes.
Okay, awesome. So awesome. I will talk about the dynamical measuring of the black hole mass in compact stellar system. So it's not basically about the barred galaxies. At the moment, I'm modeling both barred galaxies and like compact stellar system at the moment. So here in this talk, I will focus on the black hole mass in compact stellar system using JWST NIRSpec IFU. So I will start with some introduction. There are a few methods for measuring the black hole mass at the center of the galaxy. We know in the most of the massive galaxies, there are a black hole at the center of the galaxy that can affect the motion of the stars and also have a co-evolution with the host galaxy properties. There are a bunch of methods for measuring the black hole masses. Our first methods are based on the motion of the stars itself, like called dynamical methods, that itself can be include the stellar dynamical modeling, gas dynamical modeling, and MESAR. And another method is revibration mapping, which is based on the time delay between the variation of the continuum emission from the accretion disk. And it's useful, this revibration mapping. It's doable for those galaxies that they have AGN at the center. So the advantage of this revibration mapping compared to the first dynamical modeling is for revibration mapping, we can go to distant galaxy, but for the dynamical methods, we have to only focus on our nearby universe because we need high resolution spectroscopy to be resolve stellar kinematics. There are a few other methods like X-ray emission analysis, gravitational lensing, gravitational wave detection, for example, using, for example, in LIGO, that they can detect the merger of the black hole and can estimate the mass of each black hole, and the direct imaging that it's happened a few years ago for the galaxy, for one black hole, and also it's possible to measure the mass using the direct imaging. And so I will more go toward the dynamical modeling method. What we are using in our for black hole measurement is the stellar dynamics. For the stellar dynamics, we mainly get the kinematic of stars that they are orbiting around the black holes and try to model, the gravitational potential and extract the orbital library and try to constrain the black hole mass. So there are two different methodology for dynamical modeling, stellar dynamical modeling. One is called orbit superposition dynamical modeling, which is based on the possible orbital configuration that can map the kinematic data, both kinematic and photometric. And another method is Jeans modeling, which is based on the Jeans equation that also relate the observed velocity dispersion to the stars that we are getting the gravitational potential from them. There are other methods in dynamical approach called gas dynamic and MESAR, that in MESAR actually is the most powerful or give a very precise measurement of the black hole mass in the center of the galaxies. However, it needs very specific situations. So they are the water molecules like H2O in the accretion disk around the supermassive black hole that can emit intense microwave radiation and through a Keplerian orbit, and they can rotate in the very center of the galaxy through the Keplerian orbit. Using the Doppler redshift, we can estimate the velocity that they are rotating in this orbit and can constrain the black hole mass. However, this measurement need a very specific situation. First of all, need a very specific condition for the temperature and the density, and also need the galaxy be almost in a edge-on direction toward or line of sight to be able to detect. Maybe, I'm not sure, but only a few black holes, supermassive black holes, are constrained up to today using this method. And most of them in the dynamical approach are constrained using stellar dynamical modeling, in which actually is a very powerful method and can constrain relatively well the mass of the black holes in the center of the galaxies. So why is important measuring the mass of the black holes? There are lots of projects going on to try to detect and constrain the mass of the black holes in the center of the galaxies. And the question will be why the only mass, detecting and measuring the mass of these black holes in the center of the galaxy are very important to us. There are lots of reasons. I can talk about a few of them. First is black hole galaxy. The black hole and the galaxy host properties relation. For example, there are a bunch of scale relation in about for example, the mass of the black hole and the velocity, especially in the center of the galaxy, or the mass of the black hole and the mass of the bulge, or the luminosity. And in each of them, when we take a look, we will see a clear trend between the properties of the host galaxy with the mass of the black holes. However, most of these measurements are done for the most massive galaxies. And when we go toward the lower mass galaxies, we will see the dispersion get larger and larger, and I will talk about it. Another thing is the feedback mechanism. We know that black holes can affect because of the material, the energy that they can it will be thrown out from the black hole, that can affect the velocity formation in the center of the galaxy. So this feedback can be very important to understand the overall evolution of the galaxy. And also another thing is there are a bunch of, we can detect all these black holes, but we are not sure, we don't know how these black holes are formed back to the early universe. There are a few formation theories that I will talk about them, and that each of them predict different things. So if we want to constrain about the black hole formation theories, we need to first have the measurements of the black holes across a lot of different environments, like different black hole masses, different regime, to be able to answer how the black holes form and how they grow through cosmic time. So let's go into more detail about I will talk about more detail about the black hole formation theory. The first theory is called gravitational runaway. Gravitational runaway actually suggests in the dense star clusters, the massive stars can collide and merge frequently because of strong gravitational interaction. Okay, and this process can lead to rapidly form of the very massive star cluster. Like, for example, a few of the very massive stars get very close together and collide together and can form a black hole. And at the end, they will collapse into a black hole. So this scenario can have some prediction. First is the intermediate number of the black holes of the low mass. This is the mass of the black hole, that is the number density. So this theory predicts the intermediate number of low mass black holes. So when we come to the low mass black hole, they are not very high, they are not very low, but in the intermediate. And also it predicts that intermediate fraction of the low mass galaxies host low mass black holes. And also the black holes can host, that they are hosted by low mass galaxies, should be intermediate black hole mass, not very supermassive or like not very massive or supermassive black hole mass. The second scenario is actually population tree stars. They are basically, there is an idea that the first star in the universe, that they are formed by hydrogen and helium. For some of them, that they are so massive, they will be quickly collapsed directly into the black hole mass, after like the forming and passing some situation. If in those cases of very massive earlier stars, the early generation of the stars, that they can form the very early black hole masses. They are basically the stellar black hole mass, but they form in the very early, and gradually they grow, and they are the black holes that we are seeing here. However, in this scenario, when the black holes form from a single star, they need significant longer time to grow and accrete more materials and grow over the time. And when we see a very massive galaxy at the early universe, which JWST now is observing them or getting them, that would be questionable, that how, if these black holes are formed with a single massive stars, why some of these black holes are very massive at the end of the universe, and how they found some time to grow. So this prediction for this scenario is it basically mentioned the large number of the low mass black holes. When we go to the low mass black hole, this theory predicts a lot of low mass black holes. That makes sense because at the early universe, they form from a single massive star. Nearly all low mass galaxies should have a black hole, should host a black hole in this regime. Because of course, these kind of earlier stars could be everywhere, right? So in each low mass galaxy, we will have a black holes. And another prediction is the low mass galaxies should host low mass black holes. So when we go to the lower regime, this trend should be decreased. And the third scenario is actually the direct collapse, is that the direct collapse happens when a massive gas cloud falls under its own gravity. So without forming a first star, it will directly collapse and form a very massive black hole mass. So when it's occurred, the gas, the situation that in this scenario, the gas will directly collapse without forming a star is actually, it needs a very specific situation. They need the gas cloud should be very dense and doesn't break into smaller pieces. So it should be a massive cloud in one pieces that will be directly collapsed. But in this scenario, the very massive black holes can also form in the very early universe, because these huge clouds at the early universe, these clouds can be huge and it will be massive. So it's called direct collapse. The prediction of this theory is the low mass black hole should be rare, first of all, because if at the early of universe they are massive enough, after 10 to 12 gigayears evolving and accreting and growing, it should be even more massive. So low mass black holes should be rare. And low mass galaxies rarely should host a black hole mass. And the black holes that don't reside in low mass galaxies should be overmassive. So if we go to low mass galaxies, very compact galaxies, like dwarf galaxies, and if we find the black holes, those black holes should be overmassive if under this scenario. So there is different observation evidence for each of them, and there are lots of subjects going on. Maybe at some point all of them can be happen or no, but to understand that which of them are the dominant, like the black hole formation theories, or most successful, as you can see, we need to go to low mass galaxies. When we have in a higher mass galaxies, all these trends are quite very close together. If only when we go to the lower mass galaxies, this prediction of each of these scenarios gets distinguished significantly. Okay, and so here, this is the relation between the host mass and the black hole mass for different region of the galaxy, from 10 to 5 solar mass, 10 to 12. Only a few a few like maybe less than 10 black holes are measured robustly in low mass galaxies, like maybe less than 9. So they are the stars here that we call them. They are mainly compact elliptical or UCDs that they are here. And the question is now, there is a gap between, this relation in high mass galaxies and low mass galaxies. And the question can rise that, are these two different relation, or no, it can be a power law, a broken power law relation that start from a stronger steep and then go to the autoregime in this part to cover for the massive black hole. So, and the point is, the black holes that they are here in compact low mass stellar system are usually can contain the mass of the black holes can be up to 20% of the total stellar mass, even like 1%, and in some case 50% of the total stellar mass. It means the mass of the black hole itself can be from 1 to 50% of the black hole of the stellar mass. But when we go to a very large galaxy, like 10 to 11 and 10 to 12, the black hole, the fraction of the black hole to the stellar mass of the total galaxy is like maybe 0.01%. And so the frequency of massive black hole in low mass stellar system matter. And another thing, if we look at the stellar mass function of the universe, we can see there are still much more galaxies that they are less massive than the Milky Way when we go toward the less massive, like 10 to 9. So Milky Way is kind of massive galaxy, is in the middle, let's say in the middle, but almost massive into the middle. But when after Milky Way, the number of the low mass galaxy, the number of the galaxies with lower mass than the Milky Way increase. So it's really important to push the limit of detecting black holes in the lower mass galaxies. And also, there is also another gap between the detection of the black holes or measurement of the black holes. For a stellar mass black holes that they can be from 1 to 100 of the solar mass, there are a lots of, we can find them in the Milky Way, and we can use different tools like gravitational wave, LIGO, and different tools to detect them and measure and constrain the mass in these black holes, like the binaries. And for supermassive black holes, it's also simple. They have a strong influence in the internal kinematic in the central part of the galaxy, so we can constrain them. However, when we come to intermediate mass black holes, like 1,000 to 10 to 5, or near to 1 million, not past 1 million of the solar mass, probably 10 to 5, these intermediate mass black holes are really hard to measure and detect. First of all, if they need to have some certain condition. For example, in the dwarf galaxies, in the compact stellar system. Second, they are not massive enough to significantly impact or influence the internal kinematic of the center. And also, we have some observational challenge because of the very small effect in the velocity dispersion. However, this is a gap. If for the computing the black hole formation scenario, we still need to fill this gap. We still need to have some measurement of the intermediate mass black holes that help us to constrain the black hole formation theories. And so where we can find not necessarily intermediate mass black hole, but the lower mass black hole, like 10 to 6, 10 to 5, around that. So the answer is in compact stellar system. So here I listed a few compact stellar systems that we are working of them. 3 examples of the compact stellar system. They are low mass, and the first is UCD, or ultra compact dwarf galaxy. They are basically smaller than regular dwarf galaxy, with diameter like around 1 to maybe 100 parsec, 10 to 100 parsec, and they are more massive than the Virgo cluster. For example, this is the host of the galaxy, and this is the UCD which is around the host galaxy. So this is the effective radii of this around 10 parsec to 100 parsec, and they are slightly massive than Virgo cluster. However, there are two different formation scenario for this. One is they said that these UCD are a stripped remnant of the larger galaxy. I will show you a simulation later. Or the second formation, they say they can be a massive star cluster that formed in the densest region, and now they can be in the higher end mass of the Virgo clusters. But the point is, if we find a black hole mass, like massive black hole in this system, in this kind of UCDs, it is kind of confirmation that they are not from the Virgo cluster branch. Another galaxy, like another compact object, or compact ellipticals, that they are significantly smaller than the elliptical galaxies. However, and their radii are from like 100 parsec to a few hundred, can be even to a few hundred parsec, and they have elliptical shape, but they are really massive. Like they can be even 10 to 9 of the solar mass for that they in such a small area. So they are really compact compared to the even the elliptical galaxies. And another object are nuclear star clusters that also have very high stellar density in the center, and they provide a good opportunity for us to detect the black hole mass using dynamics, because there are lots of stars, the high density of the stars around the black holes, that they can easily affected by the mass of the black holes dynamically. And so there are also two scenarios for formation of these nuclear star cluster, that they can be from the merger, formed by the merger of the Virgo cluster and then sink to the galaxy center, or they form due to through in situ star formation driven by the inflow gas from the outer region to the central region. So we have the subsample of all these compact ellipticals now, the kinematic data from JWST. So let me show you first an example of the formation scenario of a UCD. If it's a strip nuclei, it can be also similar to the compact elliptical galaxy, that they gradually start, when they are orbiting around the host galaxy, because of the gravitational effect, tidal effect, the outer shell of these galaxies start to strip away, and this companion galaxy continuously start to losing mass by each rotation when they pass pre-center and apocenter of the galaxy, until at the end only the very central part of this galaxy can remain, which is very compact, and the stars there are strongly gravitationally bound, and finally can form like a compact ellipticals or a UCD. For those, in those cases, that they are a strip nuclei, which means that the outer part or outer shell of the galaxy is already stripped away. So in this case, in such case, it makes sense if we find an overmassive galaxy or a massive galaxy, because they were like a larger galaxy or like dwarf galaxy, or it was a larger galaxy around the galaxy host. And then after, because of the tidal effect, it's lost the majority of the mass in the outer part. So we obtain about 18 targets from JWST NIRSpec IFU data. The PI of the program is Matt Taylor at University of Calgary. This is our target, the stars here. And we can see we have in some of our compact ellipticals have around 1 kpc effective radii, and 10 to around 9 solar mass, the stellar mass of this elliptical. And we also have very small UCDs, kind of the smallest UCD observed by today. I mean, we have data from it by today, kinematic data. For example, the UCD here, that the effective radii is around 10 parsec. And these UCDs, the blue dots here, are actually the location of the Virgo cluster. So we see some of these UCDs are really close to where, or actually they are in the place that the other Virgo cluster are located. And this is a distribution of our targets on the Virgo cluster. So we use orbit superposition modeling called Schwarzschild model and to estimate the black hole mass in targets. However, before going to targets, we need to test how robust is our dynamical modeling tools. Of course, we can give some input data, a potential, and then constrain, random code to see what's output. But the point is, how reliable is this measurement? And what kind of different thing can affect in the output of the dynamical models? To do that, first of all, I talk about what we have from the observation and how we model them. And then I will talk about how we test our tools. So from the kinematic data, consider we have two sets of data. One is kinematic, one is photometric. From the IFU spectroscopy data, we can get a spectroscopy at each aperture using IFU and try to create a stellar spectrum template and extract the kinematic, like the line of sight velocity, by fitting this function called Gauss-Hebel function to the line of sight velocity distribution. We can get the line of sight velocity, velocity dispersion, H3 and H4. What is H3 and H4? Basically, we know the line of sight velocity cannot be always a perfect Gaussian. So H3s basically can tell us about what asymmetry is this line of sight velocity from a perfect Gaussian, like skewness, the concept of the skewness in the Gaussian distribution. And H4 can tell us about how peaky or flat is this line of sight velocity distribution. There are important signature of the diff. For example, H3 usually have the anti-correlation with the velocity dispersion, with the line of sight velocity, that they have rotation. And there are also, when we have a black hole, we can see the signature of the black hole in the H4 map. So getting this value like H3 and H4 as a higher moment velocity are very essential in constraining the black hole in our dynamical modeling approach to get a precise measurement. The second data set that we use is photometry, is the image of the galaxy. So the first step for dynamical modeling is make a gravitational potential, right? And for making gravitational potential, we need to estimate the 3D density of the stellar system, like the galaxy. So we have a 2D projected image. We can use first fit the 2D surface density using, for example, what we are using, like multi-Gaussian expansion, try to describe the 2D surface density. And then by assuming some viewing angles, we can deproject this 2D ellipse to a 3D ellipsoidal, ellipsoidal Gaussian. So then we can have a rough estimate from the 3D density and then compute the potential. When we have a perfectly axisymmetric system, only inclination angle theta is matter to us. So the only free parameter is inclination angle. But when we have a triaxial system, we have more angles, Euler angles, as you can see here. They need to be considered. So sometimes people say, okay, there are the degeneracy in the modeling, how we can understand which of these angles are true or no. That's a complicated case. However, in the compact ellipticals and the U series that we are going to use in later, I will say, they are roughly spherical or highly spherical, especially U series. So we can stick to the spherical or only axisymmetric models. So as I mentioned, the 3D projected model cannot explain the very detailed, for example, especially if we have a spiral barred galaxy. There are some different structure out there. So some details will be missed in the 3D projected density, but still it's possible to have a fair estimation of the 3D density of the stellar distribution. So when we get, from the kinematic and photometric, we get the 3D density of a star, we can solve the Poisson equation and get the gravitational potential. And we can also add the dark matter, the gravitational potential contribution with dark matter, and a black hole mass at the center of the galaxy. So there are a bunch of free parameters here. We are flexible to pick between them. and later we will try to change them and fit the model. So we integrate a bunch of the orbits in this potential that we made, and we make sure we have all kind of orbits. For example, hot orbits, cold orbit that they are purely spherical, or they have boxy shape, and then superpose our orbit together to make our galaxy. And at the end, we can compute the observable in the aperture and try to fit to the data. And then we need to reproduce this process thousands of the times to get a sensible or find the best fit to observation. And after finding the fit to this kinematic, we are able to constrain those three parameters that we constrain here: black hole mass, dark matter, and like viewing angles in the stellar densities and 3D density. So now, when we want to apply our modeling to the compact elliptical galaxy and the UCDs that we got from JWST, as I mentioned, we need to test how robust is this measurement, and what kind of things can be affected. So during the past year, we made lots of tests. First of all, we make some n-body realization mock model from the compact stellar system and put them in the distance of the Virgo cluster with the similar setup as JWST NIRSpec IFU. And so for n-body realization, we need to make some n-body model for the compact elliptical system and UCDs. The way that we use the Agama package, which is a toolbox, and you can do lots of cool stuff about dynamical modeling, or sorry, galactic dynamics with Agama. So we consider a density profile, and we can define the inner slope and the outer slope, try to see which kind of density profile can match an observation images. We get the photometry of the UCD and fit like Sersic function easily to that. And also we make some, using this density, we make some model and try to project it to the image to see how similar it is. And after making a density profile, considering the density profile, we can compute the gravitational potential, and then we will add a black hole potential, Plummer potential, and we can, using the potential and the density, we can consider the distribution function that can tell us about the distribution of the star velocity in the phase space. And so we use this spherical anisotropic distribution function. The parameter beta here we are flexible to set this beta if we want to have isotropic system or anisotropic system. After making a distribution function, we sample or n-body mock model from this distribution function. The position will be sampled from density profile, and the velocity sampling using the velocity dispersion derived from the Jeans equation. Okay, this is the overall process how we make a mock model, a mock n-body representation of a compact stellar system. So after making a bunch of them, this is the internal profile of the velocity dispersion. Here is the compact elliptical. We tend to around 9 solar mass, and it is a UCDs, we tend to around 7 solar mass, okay? So the black lines are those models contain no black hole mass, no black holes, the mass is 0. The red one is the black hole with 0.1% of the total stellar mass. The blue one, those black holes are 1% and 10% the green. The dashed line are anisotropic stellar system, and the solid line are isotropic. So we overall find, when we have a kinematic data, it's important what is the influence radius of the black hole, or black hole influence radius. This is the radius in which the potential of the black hole is dominate the potential of the stellar of the star component. So we can see the effect. We can see better the effect of the black holes on the motion of the stars in this radius. So when we have the black hole less than 1% or very small, like 0.1% of the total stellar mass, this radius, the black hole influence radius will fall below or resolution or kinematic resolution. So basically, we cannot constrain the black hole. Later, I will show in the detail. And yes, but for 1% black hole and 10% black hole, for this specific MOOC setup that we make, the spheral influence of the black hole can be resolved from the kinematics. So this is the kinematic map of our MOOC system. They are compact elliptical, and this side are the U series. From top to bottom, this is the 1% black hole, isotropic, and 1% black hole, anisotropic. As we see, when we have a 10% black hole and it's isotropic, we have the most line-of-sight velocity dispersion in the center, and also the effect in the H4 map. So it will be easier to catch the black hole mass in this kind of system. But you see, for the 1% black hole, the elevation in the velocity dispersion in the center is really weak. However, still in our model, I will show you we can constrain the black hole even with this slight elevation, but anything below that, it's not possible. So we add noise to these are noise-free kinematic map. We add noise to these kinematics and run our modeling with different kind of setup. So we use Forest-Time code. It is part of Agama Galactic Dynamic Tool package, as I told you already. Our models are fairly simple. We have a stellar component and a black hole mass, a black hole. We don't include the dark matter. First of all, most of the there is no effect, no evidence for dark matter in U series. And for compact ellipticals, like 50-50, in some of them, they found the effect of the evidence for dark matter, and some of them no. However, the kinematic coverage of our data is very small. It means it zooms in the very center of the galaxy. The kinematic cube is 1 arcsecond to 1 arcsecond. So it's very, for example, consider the effective radii of a compact elliptical is around 1 kpc. And we can only cover like up to maybe 50 parsec or up to 100 parsec. So in the very central region, it's hard to see the effect of the dark matter. So we are kind of fairly sure that we can ignore the dark matter because we cannot constrain. The kinematic data cube is extremely small. However, we have some tests about the dark matter as well. I'm not going to talk about it now. But anyway, these models are only a star and black holes. So this column is about the compact elliptical. This row and this row is UCDs. The first column is 10% black hole, and the 1% and 0.1% black hole. This is actually the parameter grids, this mass-to-light ratio and the black hole mass, which means when we are modeling, the black hole mass and mass-to-light ratio will change through this grid, okay? So there are 3 levels of contours, indicate 1 sigma, 2 sigma, and 3 sigma level, uncertainty for our measurements. The red contours are for an isotropic model, and the blue contour are for the isotropic model. So our conclusion is, as well as we have 1% black hole in our system, we can still accurately constrain the black holes. You see, this is the base fit, this cross, the base fit model. But if you consider this, like the first contour is 1 sigma model. So usually the base fit model is in the 1 sigma. The true value, this vertical and horizontal, is the true value of the MOOC model. When we are modeling our MOOC, we know what is the real black hole, right? So this vertical line, and this is the true black hole. So in C, when we have a more massive black hole, we can accurately, or best fit model at 1 sigma contour, recover the black hole mass. For 1%, it's still large uncertainty, but still this gray line is in our 1 sigma contours. So we still can accurately constrain the black hole mass. But when we go with very low massive black hole, 0.1% of the stellar system, you can see we cannot detect like the outer limit, lower limit for the black hole mass. So basically, we only can provide an upper limit for such cases. And now we will go to the observation. This is the first target, UCD 736 in Virgo Cluster. As you can see, it is located well between a few other massive galaxies like between the three, and it is really small, and the effective radii of this UCD is around 14 parsec. This is really small. And so Solveig, she's a master's student in University of Calgary that she will graduate sometime soon and start her PhD there. She is responsible to extract the kinematic map for these UCDs. And so this is the velocity dispersion and H4 map. The H4 value are extremely small, the value, but in the only in a few central beams, they have some values that we can rely on our modeling. So we applied our modeling, and we could catch, we clearly could detect a black hole this is the black hole mass and the mass saturation of modeling. And we found that these black holes, the fraction of this black hole to the total stellar system for this UCD, it's somewhat between 6 to 10%. This is really an overmassive black hole rising in the core of this UCD. And this UCD is one of the, in context of the mass, is around 10 to 7.4. It's not very massive. So this fraction can be like from 6 to 9, and this is the base fit of the velocity dispersion. The black dots are our models, and the red line is the base fit model. For this plot, unfortunately, I don't have a model with zero black hole mass, but when we have a zero black hole mass, this red line will be like that, will be how they go to between 25 kilometers per second. And only existence of black hole can jump up this red line in the velocity dispersion. So if I want to locate only around, still about uncertainty, I don't want to talk about uncertainty. It is around like 0.6, but I want to only put the roughly where this UCD will be located in this map. It's in the 1% black hole mass fraction trend. That, as we discussed, that this area, this especially red area around here, are the area that can be supported by the direct collapse in the context of the black hole formation theory. And there are previously only a few very robust black hole detection in the UCDs. They were like 5 of them they found here in these studies. As we can see here, first of all, this UCD is the smallest UCD that up to date is kind of detected. It is, and it's overly massive. Also, the mass of the black hole itself is lower than these, but if we can consider the mass of the stellar system itself, the fraction is 10%. And look at this around here, that's contained in this kind of M black hole MUCD relationship. So we hope this is the first target. We are modeling some other target, but as we are not, the outcome is still uncertain. We are working on them, and we hope in a few months they will be ready. At least we have some sensible measurement with good estimation in uncertainty. And we hope to be, by increasing the black hole measurement in this regime, we hope to increase the constraint on the black hole formation theory, and even further about the formation scenario in UCDs, compact elliptical, and nuclear star cluster. So I will stop here. I don't put any conclusion. The project is ongoing. Maybe if we could, like, maybe next year after the project, I would be happy to talk about it and share the final result. And if there is any question, I will be happy to answer. Thank you.
Question? A lot of black hole people. Yeah, I'll make one. I took some notes. So in the beginning, are there questions from Zoom? So I have a technical question. So how much does assuming or not Voronoi binning affect your kinematic results?
Oh, that's a very important question. Okay. I didn't put the map here, but okay, I tried some in our paper that we are submitted. We try to rebin the different signal to noise ratio with different signal to noise ratio. So for the Voronoi binning, we need to also put a signal to noise ratio target. I mean, the target signal to noise ratio before Voronoi binning. So, for example, for the signal to noise ratio, we found that when we have signal to noise ratio below 20, the measurement of the black hole mass are kind of only for 10% black hole mass, we can have a robust measurement when we have like signal to noise ratio to like below 20, like 10 to 20. And we cannot recover the black hole mass for 1% of the stellar mass. If only the signal to noise ratio, it's increased like more than 30 per each Voronoi beam, then we are able to constrain the even 1% black hole mass. So it is exactly what the Ripley asked about our paper. So I run a set of models with different Voronoi beam, different signal to noise ratio, and we found that for the less than 20, for 10, like signal to noise ratio 10 to 20, we can measure the black hole mass for 10%, very massive black hole mass, but we are, for the lower mass black hole, like 1% of the stellar mass, we are not able. So something, according to the literature, any resolution between 20 to 30 is really, it can be enough for detecting black hole, have a fair estimation of the black hole. For this kind of, for this mock you see that we have, in outer, for the central being, for the central pixel, the signal to noise ratio even can be up to 70 to 80. So we kind of, have a confidence for the measurement of the kinematics in the very central beams.
Everyone's very cold. So I have a basic question, one more from the beginning. You said that there are two kinds of UCBs, and you said that measuring the black hole masses would help constrain one or the other. Can you go into a bit more detail about this? And then we have a question from Patrick.
Yeah, I think I'm not expert about the formation scenario in the Virgo clusters, but for the massive black holes in the central, I didn't see like a strong evidence for a massive black hole in the center of a Virgo cluster yet. I don't know if maybe some intermediate, but for the massive black hole in the center of Virgo cluster, there is not a strong evidence for that. So it means if there is a massive black hole in the center of this object, this is not a Virgo cluster, because the Virgo cluster cannot contain this massive galaxy black hole in the center. So this can be some pervious like companion galaxy that stripped, because of the tidal effect, the outer shell of the galaxy is stripped away. So we have a massive black hole in the center of this galaxy. And yeah, this is the general idea. When we have a massive like black hole, it's most probably it's a strip nuclei rather than be a dwarf. I mean the Virgo cluster.
Great.
Yeah, so there are a lot of uses without a black hole in the center. There is no detection of the black hole. So in those kind of cases, yeah, that could be true, to go to further investigation to see maybe they are just the outlier of the Virgo cluster, not a pervious companion galaxy.
Carlos?
So, hello, can you hear me?
Hello. Yeah, sure.
Yeah. So, thank you, Behzad, for the talk, and I also have a question regarding the Voronoi beams, because I'm also working with dynamical models, so I'm kind of interested in the subject. But does the number of kinematical beams impact your results? Do you have an idea about this? I mean,
Yeah,
minimum number of Voronoi beams in the data should be enough to constrain your black hole mass or something like that?
so there are a lots of other parameters. That's for example, the size of the PSF, the magnitude of the line of sight velocity distribution, and the gradient of the line of sight velocity distribution. So we cannot say a number for that. It's really depend on the case study, the PSF of the instrument, even the PSF of your image, and the number of the pixel you have, the signal to noise ratio. It can be done with like this UCD that we made. We have only 10 beams, and we don't use the Voronoi. It's not 2D dimension, it's only one dimension, so 1D radial dimension. When you don't have enough Voronoi beam, in 2D Voronoi beam, you can easily use the 1D dimension beam, and in the radius, for example, each shell of the radius will be one beam, and 10 or like 10 to 15, something like that, around 10 beams can be, 10 beam along one axis, that give you the sense of the change in the velocity dispersion, not 10 beam in overall. So something around 10 beams in direction one axis that you can see clearly the gradient of the velocity h4, h3 in one axis. I think you can have a sense of the measurement. However, it's not a number. There are lots of other things. How about the like PSF size, your kinematics, the signal to noise ratio, and different things. Yeah. But if you have, like, for your own case, if you have now trying to Voronoi beam and you're struggling to see if it's possible to constrain the black hole mass, now that would be great if you could just contact me. I see your kinematic map visually to according to my experience, to get a sense that how good is kind of for constraining the black hole mass using dynamical models. However, if you just only want to use dynamical modeling, not black hole mass, for example, only the dark matter mass in the outer region, you need to have the Voronoi beam in the outer shell of the galaxy. If you don't want to care about the dark matter, also only care about the total mass ratio or internal kinematic of the stars, you can have a large Voronoi beam, not very resolved in the center. So it's very depend on the specific case study and what you want to get from dynamical model.
So really interesting. Thank you. Yeah, I will send you an email later, so then you can talk more about this. Yeah, interesting. Thank you.
You're welcome.
More questions from Zoom? From the audience? Okay, I have one last one, but it's a bit related to the second one. So what happens then to the dark matter of the dwarf that leaves behind the UCD?
Oh, that's a very important question. And, the point is, according to the simulation, some n-body simulation, they suggest when they are getting tidally stripped away by the galaxies, because the dark matter is in the outer shell, then they are less bound in the center of the galaxies, less gravitationally bound, the dark matter will be stripped away at the first place. They are distributed more in the outer region of the galaxy, and only in the very central part of you see the simulation, in the very central part of the galaxy, they are strongly gravitationally bound, so they could be. So more or less, the dark matter are distributed, according to some simulation, they are distributed moreover in the outer region. And in the tidal interaction, actually the dark matter, the particles in n-body simulation, they will strip away in the first place. So that's why for the UCDs, they said there is still no evidence for dark matter. However, for compact elliptical, depends on the force and how close they are to the host galaxy. It's like 50-50. In some compact elliptical, there are strong evidence for dark matter, in some no. But for UCDs, I guess because they are extremely small, still we didn't find any strong constraint on evidence of the dark matter. And again, back to the question, to simple answer, because the dark matter will be stripped away even before stars, I mean, at the first place, according to some embodied simulations.
So thanks a lot, Behzad. If there are no more questions, let's thank Behzad again.
Thank you, Anna, and thank you everyone for your attention.
Great, nice work.